iron thiocyanate. We used Beer's law and UV vis spectroscopy. So everybody went over the theory, a little bit of UV vis spectroscopy, and by a little bit we went as deep as we're going to go into the theory. Then the two important equations that I don't think you'll have to have memorized, but you should have seen them before and not be surprised, is E equals hc over lambda, right? Right, where this is Planck's constant. You remember this. Speed of light. Yeah? I think so, yeah.
Or at least, well, at least the constants that you
Yeah, you'll be given the constants for sure. What this means, the main thing that it's important to know that you might want to just have aware of is that wavelength is on the bottom of this equation, right? So that means that wavelength and energy have an inverse relationship. So that means that the bigger the wavelength that light is, the lower energy it is. Does that make sense? Just let it sink in. The other one is Beer's law. This one may be a new one.
Well, I think we went over it.
Well, yeah, but I mean, you didn't go over it in Gen Chem, maybe.
Fair enough.
None of this is new. This is all we do. So absorbance equals a coefficient times the concentration times the path length of the cuvette. So basically, it's a linear relationship between concentration and absorbance. So this is, and so if Beer's law relates that's the main thing to know about Beer's law. So it relates absorbance and concentration. So this is the constant. Sorry. And this is a constant. This is the length of the cuvette that you put in here, alpha. Something that they talked about in the lab theory that we didn't really talk about is absorbance versus transmittance, and they asked a few questions about it in the review of the post lab. I'm not sure how it's important. Just remember, it's the opposite, right? Transmittance is the light that goes through. Absorbance is the light that your sample absorbs, so they're the opposite. So don't get confused about that. It's pretty simple. We didn't talk about it during the lab, but it's mentioned in the materials for the lab.
Yeah. But yeah, I mean, it should be relatively straightforward. But if you do have any questions with that sort of thing, please let us know now. And remember, when you come to the lab practical, we are merely there to babysit. We are not there to answer any sort of questions unless you're having some type of troubles or something. And also, I will reiterate this with everybody here. Please make sure you come absolutely and fully dressed and everything. Make sure, like, you have long pants.
Fully dressed, everyone.
Fully dressed. Long. It's not one of those no shirt, no shoes, no. It's one of those no shirt, no shoes, no service things.
No shirt, no shoes, no service.
So, and pants too.
Yeah.
So long pants, closed-toed shoes, ballet flats are discouraged, like where they are, like your shoes aren't, like where your bare feet aren't fully covered. So make sure you have something that fully covers your feet. Also, with regards to shirts, at least, like, just bring over a t-shirt or something like that. At least t-shirt length.
It will probably be hot.
It will probably be hot, but that's part of the deal.
Okay.
We don't come dressed like this every day.
Yeah, it's really fun. Science is great.
Science is super awesome.
It's really great. Okay. Lab 4, Pierrette. Works the same as the Moore pipette. Guys, remember it's got a stopcock on there. Cross is closed. Remember that? I would go ahead and pour a little, if you end up using it, pour a little think of water water or something in there ahead of time to make sure that your pipette isn't leaking or anything like that. Because those of you that had me know that I told you to put a little bit of liquid in there. Make sure your pipette's not leaking. But yeah, process those, got a stop cock. Again, like I said before, the volumes to the hardest place on the burette, it's 0.00. In that lab, we did KSP. So everyone remember, the one thing I could think that would be tricky about KSP is that it's only a soluble ions, remember? It's the solubility product. So you need to make sure to look at the phases if you're given an equation or something like that. Make sure that you look the phase of matter on the equation and make sure that you are just doing the ones that are in solution. Don't do a solid. So we did KSP, which you should have remembered, just the soluble ions. Okay, and then we plotted delta G, right, and related it to ln K. So we plotted and we did that by so this is our M. If we do y equals mx plus v, M is equal to negative delta h over r, x is equal to 1 over t, and p is equal to delta s over r. So that's how that plot worked. Because we just took delta g, then turned it into a form where we could relate everything, simple y equals mx plus b, like you guys did in high school. The change in entropy.
Also, you do need to remember what's the difference between entropy and enthalpy. That is another thing that's pretty important. So enthalpy is just the amount of disorder that's happening. That's in
Entropy.
I said entropy.
I saw scared. I saw
I
scared students.
I really misspoke. But
okay.
Entropy.
That was
is
disorder right there.
Yeah, that was disorder.
Yeah, that was good. We just had a little entropy moment.
But yeah, delta S is the entropy, and then the delta, which is basically the amount of disorder. I.e., if you have a reaction where you have just a whole bunch of densely packed solids, and it turns into a whole bunch of gas and something like that. That's an example of getting a whole bunch of disorder. Or if you're dissolving an ion or something like that, if you have a salt that's solid and then you put it into a solution and it's dissolved, that also means you're getting some disorder. But there's a difference between solubility and turning from a solid into a liquid. Basically, what it means, if something turns into, if you're having matter that's turned into a liquid, basically you have a block of something, like if you have a block of ice, and it melts into water, that's one thing. But if you have a piece of salt, like sodium chloride, and you throw that into water, that dissolves into water and dissociates and stuff like that. That's not the same thing as solid water turning into liquid water. So that is something that I taught on writing. Slight difference. Even with sugar as well, if you have a block of sugar and you throw that into water, the sugar molecules aren't breaking apart, they're just simply dissociating with each other and associating with the solvent. So I think that's just kind of a minor difference, but it's just something that I kind of picked up as well.
For that, is there an increase in anything? Or like entropy or enthalpy?
What's the entropy and enthalpy change for the dissolution of sugar?
And
Oh,
is there?
Is there one?
I would say that there is a change in like there's a change in, the entropy is always going to be the same. Like when you have like hot water, I guess, if you have hotter water, sugar dissolves a lot easier than if you just have colder water. So there is definitely going to be that kind of relationship with that. But yeah, there is entropy and then there's enthalpy involved with that process. I can give you the full details about that off the top of my head.
Yeah, it's a hard one. So lab 5, our big technique, I think, was filtration. And so, let's see. For filtration, just go over if you don't remember all the nuances of that, just look on lab 5. They have a little PDF. It's about 2 pages on filtration. Just tells you, you got to fold up your filter paper, put it in a Buchner funnel, weigh it beforehand if you've got a solid. And then to remind yourself that you weighed it, you can tear off the corner, but you need to tear off the corner before you weigh it. Anyways, so let's see. So there's a piece of vocabulary that I wanted to go over because I thought it might trip you guys up, which is if we have a filtration. Do I have a book marker in my pocket?
I think you might.
Okay, so if I'm gonna have again expertly rendered in 3 dimensions this time. I know. So okay, this is my solid. You can tell because I just told you. And here, okay, so this is my solid that I want. This is my beaker right here, and I'm going to pour that over a Buchner funnel. Okay. It's like you're there, right? It's like it's really happening. Okay, so what I'm going to do is that I'm going to try and separate out my solid. So this is desired solid.